Hello, welcome to yet another graduate level classical mechanics video from Dr. Viv. We're going to be discussing in this lecture and the next one the very famous formalism known as the Hamilton-Jacobi formalism. So what happens here is that we pay attention to the entire trajectory in phase space and try to solve the problem by finding a canonical transformation that takes you from one point to the general solution. So what is this miraculous method? So it, as a brief introduction, let's suppose that we have we have a dream of going from, I call this the pipe dream of classical mechanics. The pipe dream of classical mechanics consists in going from uh, some old variables PQT. When I say PQT, I mean there are n of them called pi, n of them called qi, and then time to some new coordinates, capital P, capital Q, and T, in such a manner that the new coordinates have constant momenta and constant position. Now, is this even possible? If it is, then the problem is trivially solved because the solution to the problem is that pi's are constant and qi's are constant. We'll call the constant pi alpha I and the constant qi beta I following tradition. So these are all constants. And we have solved the problem. Now, of course, such a transformation, how do you know if it exists or not? Now, if you make this transformation to the new coordinates, then you also get a new Hamiltonian, which we've been calling the Hamiltonian. So the Hamiltonian, K, is equal to the old Hamiltonian plus some partial derivative of the generating function f. It could be of one of the four types. You have to see my previous video to understand what I'm talking about, because the four generating functions of type f1, f2, f3, or f4 could be used to create this canonical transformation that takes you from the old Hamiltonian H to the new Hamiltonian K, sometimes called the Hamiltonian. In terms of that Hamiltonian K, the new momenta qi dot are just going to be del k by del pi using Hamilton's equations with respect to the new Hamiltonian K. Well, if k is 0, let's just suppose that k is 0, then this is also going to be 0. And then the second set of Hamilton's equation, pi dot is negative del k by del qi, is also automatically satisfied. So we can actually achieve our pipe dream if we simply set the Hamiltonian to be 0. Now what is that? That gives you that h plus del f over del t equal to 0. Now Jacobi liked to use f2 generating function, type f2. Now remember that f2 is a function of the old coordinates and the new momenta. So in terms of that, the old momenta can be written as del f2 over del qi. If you go back to the previous video, you will notice that these are the transformation equations for the f2 generator. So we can write this equation, this very important equation, as follows. We can write this as h of, this time I'll write all the q's out in detail, q up to qn, the partial derivative of, instead of writing the p's, I'll write it as partial derivative of f2 with respect to qi, q1 all the way up to qn, and possibly of time, plus del f2 by del t equal to 0. So this awesome looking equation is known as the Hamilton-Jacobi equation, except it's customary to call f2 by the symbol s. And this S is sometimes called Hamilton's principal function. So the full set of Hamilton-Jacobi equations can be written in abbreviated form as follows. I'll write the partial derivative with respect to time first. That's usually done. Del S by del T plus H of all the Qi's, the del S by del Qi's, and T is equal to 0. This is referred to sometimes as the time-dependent Hamilton-Jacobi equation because the T does occur there. Notice that because time is present, energy is not necessarily conserved, which is a very useful feature of this method. You don't have to have energy conservation. All right, so that is already looking very weird and very strange. Now, if further the Hamiltonian does not depend on time, then you can write the Hamilton's principal function in a separated form. So in the projectile motion problem, that's true. So if H is time independent, then we are going to end up having S of Q alpha T is going to be some quantity W of just Q and alpha minus alpha 1 T. So what I'm doing is I'm calling this my alpha 1 all the way up to alpha n, because the partial derivative with respect to of F2 with respect to Qi are your momenta, which are constants. So I'll call them alphas. So these are the constant momenta in the problem. Of them, there's one special momentum that is dedicated to time, so that gets taken out. There's no parenthesis after that. I should not have put a parenthesis. Let me reach for my eraser. This W here is called the, now each of these things is so important that they have their own names. This is called Hamilton's characteristic function. Hamilton's characteristic function is something that depends only on the old coordinates and the constants of motion momenta, which you get by this procedure. So in the concrete case of the projectile motion, we'll see all this playing out in real time. Right now, just think of it as a formalism. So what are we going to do? What is the actual method of solving problems by the Hamilton formalism? So let's just outline this. It's a very systematic, methodical procedure. First thing we need is we need to set up the Lagrangian as a function of Qi dot, and T, and from that we need to form the Hamiltonian. Now each of these is a significant step, but in this new formalism, that's just the first step. The second step is to set up the time-dependent Hamilton-Jacobi by setting the momenta Pi equals del S by del Qi. And then we can use the technique of solving this partial differential equation. We can use a technique of separating variables. Each of these steps will be done for the projectile motion problem. And that will give us the function S. Once we have the function S, we can then do the partial derivative with respect to alpha I to give you beta I and set them equal to constant. This will give you n algebraic equations in n unknowns. The fifth step is to solve for the momenta, for the positions, alpha I, beta I, t. Then we can use the initial conditions, express alpha I and beta I in terms of the initial conditions. And the initial conditions are that pi0 is del S by del qi0 at time t equal to 0, and beta I is del S by del alpha I at time t equals 0. The seventh step is, once you have that, you can now evolve the equation in time. And obtain your S. And then you set del S by del Qi equal to Pi, and you're able to get now the momenta. Pi equals Pi of Qi0, Pi0, and time. And then lastly, the eighth step, when you have done with all this, you can find finally the energy of the system, which is negative del S by del T. Any problem, no matter how complicated, can be solved by this 8-step procedure. And some of the problems that you can solve with this method are frightening. You can solve, for example, Atwood machine with one of the blocks swinging as it goes up and down. So you can solve any problem of any complication. That particular Atwood machine that swings as it goes up and down does not conserve energy. So you don't have to conserve energy. Now, there might be instances where the variables that you have can actually separate themselves, because you can have cyclic coordinates, in which case the Hamilton's characteristic function is said to be separable. So let's see what happens when you have the separability. The projectile motion example, you will have separability. So let's just look at that a little bit. So the Hamilton characteristic function, the QIs in that W are said to be separable if the following conditions are satisfied. If I can write the W as a sum of different W's with just Q1 in the first one, just Q2 in the second one, and so on. In other words, you can write it as a sum from I equals 1 to n, Wi, Qi, alpha 1 up to alpha n. Now, this complete separability is, of course, a unrealistic prospect. Sometimes you may have just one of them that's separable and not all of them, in which case you have to have partial separability. So then the Hamilton-Jacobi equation becomes something like this. So h of Qi del W by del Qi, and then alpha 1 up to alpha n, that's the general case. It becomes h of Qi del W dW I by dQi, and then you have alpha 1 up to alpha n equals alpha I. So you have n equations like this, because of the separability. Now, if you have a cyclic coordinate, then you have a further simplification. So let's look at that's if you have Qi is cyclic. Cyclic means Lagrangian does not have Qi in it. So del L by del Qi is 0, what happens then? In the projectile motion problem, as you know, the Lagrangian will not depend on the x coordinate. So you have cyclicity in the x direction. So that will show up in this condition here. So let's just say that you have one coordinate that's, suppose you have just one coordinate that's non-cyclic. So let's say that all Qi are cyclic except for one coordinate, except Q1. Let's say Q1 is non-cyclic. Then what you can do is W, which can be written as a sum of I, Wi of Qi Pi. So I can write this as del Wi over del Qi equal Pi, because I can get the momenta by that procedure. And that's going to be alpha I. So I get Wi equals alpha I Qi, except for 1. So that's a great simplification. So the time-independent Hamilton-Jacobi, with the time taken out, because the time is taken out if I have that feature. So I'm looking at just what's left after you take out the time. So the time-independent Hamilton-Jacobi is going to look like this: h of Q1 del W1 over del Q1 alpha 2 up to alpha n. So alpha 1 doesn't appear, equals alpha 1. So this can be solved for W1. And then finally, we can write W equals W1 plus the sum I equals 2 to n alpha I Qi. Now, that's the procedure if all of them are cyclic except Q1. That's, of course, rarely going to happen. So if only you have k of them k less than n to be cyclic, then this procedure will be less rewarding. So you're going to get W equals W1 plus Wn minus k. So these are the non-cyclic guys. And then the cyclic ones will be I equals n minus k plus 1 up to n alpha I Qi. That's the general procedure. I've given out all this theory in lightning speed because I really want to get into solving the basic problem, which is the problem of projectile motion, which is what we're interested in this video. So what I will now do is keep this cheat sheet here so we can do all the steps carefully as we solve the projectile motion problem. So the general projectile motion problem, of course, without air resistance or anything, first. So you're going to have, let's draw a little figure here. One thing to keep in mind is that because the Hamilton-Jacobi formalism is occurring in phase space, it's going to see the entire trajectory at once. So it's got a huge amount of intelligence. So as a result of that, let's define all the terms for the entire trajectory before we start. So we're going to see some interesting features along the way. The range of the projectile is usually called by the letter R. The projectile is going to be launched at some initial velocity V0. We all know how the solution is going to go, so I would like you to keep all that in mind, those elementary things which you learned from basic physics. So at t equal to 0, we'll take the initial condition that x and y are both 0. That is to say the projectile is launched from the origin, O. The x velocity is V0 cosine theta, and the y velocity is V0 sine theta. Okay, the first step asks us to form the Lagrangian and then the Hamiltonian. Let's do that. Let's do it in 2 seconds. The Lagrangian is kinetic minus potential. Potential is just mgy because gravity acts straight down. And then the Hamiltonian, you can easily show, is just going to be px squared over 2m plus py squared over 2m plus mgy, where px is del L by del x dot, which is mx dot, and py is del L by del y dot, or my dot. Done. So we've got the Hamiltonian. Now observe that x coordinate is cyclic, since so x is cyclic. So I'll say observation. Cyclic coordinate means that the Lagrangian does not depend on x, and neither does the Hamiltonian. We also note that h is time independent. So the second observation is that h is time independent. So we can use this business of writing it as the Hamilton characteristic function minus alpha 1 times t. What we're going to do, since the momentum is conserved in the x direction, we're going to call alpha x the x momentum. And we're going to call alpha 1 the total energy. Because if h is time independent, the total energy is conserved. That's the x momentum. Momentums in this formalism are indicated by alpha, and the coordinates indicated by beta. These are called action angle variables for that reason. So anyway, I have these alphas and alpha x and alpha 1. So following the protocol of separability, the part that comes out is going to be alpha x qx, which is just x, alpha times q, plus the stuff that's not cyclic with respect to y will remain as a characteristic function w of y, and then this part alpha 1 t will also come out. So I can write my therefore Hamilton principal function s will be equal to minus alpha 1 t plus alpha xx plus the Hamilton characteristic function only w of y. So that is the this you get from separability ansatz that I just discussed earlier. Very well. So now the time dependent Hamilton-Jacobi equation can be written. Let's write it. Del S by del T plus H of X, Y, del S by del X, del S by del Y, T equal to 0. So that's the general equation. Now what do you get? Because S has got that appearance, del S by del T is just negative alpha 1. The Hamiltonian is right there. So all I have to do is stuff in these things inside the Hamiltonian. So alpha 1 plus del S by del X. The X momentum is just alpha X. So that's going to give me alpha X squared over 2m. Now for del S by del Y, I have to write the derivative with respect to y, because when I do del S by del X, I just get alpha X. But when I do del S by del Y, these two terms won't contribute, but this term will contribute. It's the derivative of W. So I get W prime squared over 2m, and then I have mgy all by itself equal to 0. So that's an equation I can do something with. In fact, I can solve for W prime. So let me do that. So W prime squared over 2m equals alpha 1 minus alpha x squared over 2m minus mgy. So I'm taking everything to the other side other than W prime squared over 2m. I can solve for W prime by taking the square root. And multiplying by 2m. If I multiply by 2m, this will get a 2m, but that won't. So I have, and then here I'll get 2m squared. Weird looking. But that can be integrated. So that's the next step. I'll integrate this. So carrying on this work here, I get W equals the integral of the square root of 2m alpha 1 minus alpha x squared minus 2m squared gy dy. Well, sometimes you really don't have to do much at all. The W is there. You don't really have to integrate it because the really interesting things are derivatives of W. For example, what is beta 1? By the general principles of the Hamilton-Jacobi method, beta is del S by del alpha I. Remember that beta essentially solves our problem, because if you have the betas, you know how the system evolves in position. And if you have the alphas, you know how the system evolves in momentum space. So you essentially have the problem solved. So the next step is to find the betas. Let's do that. And let's also use initial conditions. That's what we're going to do next. So I want to just keep this over here, our cheat sheet. So we have to do this now. Separating variables, we've done, so we have solved this. So we have solved. Why have we solved S? Because S is equal to minus alpha 1 t. Let me just go ahead and maybe think of, I don't want to write it because it'll be additional writing. It's just minus alpha 1 t plus alpha x x plus whatever I wrote here there. So we have essentially solved for S. We have finished this step. Now we are going to take the derivative of S with respect to alpha I to find the beta I and see what happens. So we're in step 4 now. Maybe I should have written all these steps out. Step 1, step 2, solve by separating variables for step 3, and this is step 4. So what we're going to do is take the derivative with respect to alpha 1. Well, that's just t, minus t rather, plus there is no alpha 1 there, but there's an alpha 1 there. So we are stuck doing the derivative under the integral sign. So when I take the derivative of the square root, it goes downstairs. But then I have to take the derivative of the inside function, and that gives you contributions upstairs. So upstairs, the derivative with respect to alpha 1 leaves us with 2m. So I'll get 2m times dy. And then when you take differentiate the 1/2 power, you get 1 over the 1/2 power in the denominator. So that just gives me 2 times the square root. So the derivative of d by dx of x to the half is 1/2. X to the minus half is what I've used, basically, okay? Just to keep that straight. 2m alpha 1 minus alpha x squared minus 2m squared gy. Okay, I can take beta 1 and t on that side. So I get beta 1 plus t. This is common. We always do this. Beta 1 and time are kept together. These frequencies are always kept together with the initial angle. That's the initial angle, and this is the frequency times t. Frequency turns out to be 1 in this case. Integral m dy, the 2 cancels out, divided by the square root. Well, this thing is not that frightening. It may look awfully frightening, but it's not. Most of it is constants. 2m alpha 1 are and alpha x squared are constants, and you just have a variable y. So simple u substitution should do the trick. Actually, I prefer always u squared substitution because I don't like to keep the square root of u. I'm allergic to square roots. So whenever people do u substitution, I say, why bother? Do the u squared substitution. Because if you do that, then 2u du will be equal to negative 2m squared g dy. The 2 cancels out, and I get dy, which is what I have to eliminate here, is minus u du over m squared g. So let's continue integrating. So I get beta 1 plus t is equal to integral, now in the u variable, in the terms of the u variable now, m times dy, which is negative u du over m squared g divided by u. So no square roots at all. And lo and behold, u cancels out, m cancels out, and this can be integrated minus u by mg. Don't put a constant of integration. That constant of integration is already here. It's beta 1. So this gives me u equals, multiplying both sides with negative sign and mg, I get negative mg beta 1 plus t. But what is u? It is the square root of all this. I don't want square roots. I'm going to square both sides. So this is equivalent to u squared equals m squared g squared times beta 1 plus t squared. Oh my goodness, are we ever going to get projectile motion or not? It's looking more and more complicated, but it'll actually work out, don't worry. So now we'll substitute for u squared, which is over there. So I'm going to get 2m alpha 1 minus alpha x squared minus 2m squared gy equals m squared g squared beta 1 plus t squared. Now, the reason it looks so complicated, this is actually Galileo's result. I can see it, but because it's got all the right features, it's got y equals quadratic in time. But what's all this junk? We need to somehow get rid of it. So that's where the initial conditions are going to help us. Let's now start putting the initial conditions in. So initial conditions. Remember, at t equal to 0, the projectile was at the origin. So at t equal to 0, what was the value of alpha 1 though? Alpha 1 was the energy. And that energy at the origin was entirely kinetic because it's not lifted off the ground yet. So there's no potential energy. So at origin, you only had kinetic energy, no gravitational potential energy. So that allows us to substitute for alpha 1. Now, what about alpha x? The alpha x, as you all know, does not change. The x momentum never changes. So whatever it was at time 0 is what it will be forever. Let us find out what it was at time 0. At time 0, the x velocity, alpha x, was mv naught cosine theta. And that remains the same. for all time. Also, y here was equal to 0. So we can substitute all these three things there at t equal to 0 and figure out what beta 1 is. Okay, let's now solve for beta 1. This gives us at t equal to 0, I have 2m times 1/2 m v naught squared. I've substituted for alpha 1 now, minus alpha x squared, which is this m squared v naught squared cosine squared theta is equal to, that's 0, is equal to m squared g squared, t is 0, so that's just beta 1 squared. 2's cancel out. Now observe here, m squared v naught squared is common. 1 minus cosine squared theta equals m squared g squared beta 1 squared. Well, I can literally see you screaming 1 minus cosine squared theta is sine squared theta, and I'm listening to you. So I'll write it as v naught squared sine squared theta equals g squared beta 1 squared. Now solve for beta by taking the square root sign, but be very careful. It's a plus or minus. So beta 1 equals plus or minus v naught over g sine theta. Now the obvious interpretation of this is the time taken to reach the highest point. So beta 1 is in fact the time taken to reach the highest point if you take the absolute value sign of it. So here's the physics. It's always important to keep in mind the physics, especially in simple problems like this. In more complicated problems, you won't know what's happening, but here, at least it's all very clear. Beta 1 is the time needed to reach the highest point. Because when you reach the highest point, the y component of the velocity is 0, and we have vy equals vy naught minus gt. If you set that equal to 0, it tells me that t equals, we'll call this t half, because it's a halfway point. T half equals vy naught over g, and vy naught is just v naught sine theta over g. So that's the physical interpretation of this result. Let's now substitute the initial conditions back in equation 1, which is this equation that I forgot to call equation 1. Did I forget to call it equation 1? Probably did. So I meant to call this complicated looking equation, equation 1. Let's go back and substitute it all in there. Put in equation 1. So I'm going to get everything I had here. So it's going to be v naught m squared for general time. This is not for 0 time, but for any time t greater than 0. So I get m squared, just like before, I get m squared v naught squared sine squared theta from there, just like I did there. But this time I won't have this term be 0, so it's going to be negative 2m squared gy equals all the stuff to the right with the beta put in there. Beta 1 is that. M squared g squared. I'm going to put plus or minus because I'm afraid I might miss out on important information if I lose the negative sign. So I've put it back in equation 1 and it looks like that. Can this be made any prettier? The answer is yes. I can sort of see cancellations happening if I bother to unwrap the square root. So let me do that next. So I get m squared v naught squared sine squared theta minus 2m squared gy is equal to m squared g squared over here. And then when I expand the square root, that's a plus b squared, that's a squared, the plus or minus will not matter. So it's v naught squared over g squared sine squared theta plus 2ab. There the plus or minus sign will matter. So it's going to be plus or minus 2 v naught over g sine theta times t plus t squared. Okay, I can sort of see the cancellations because the g squared is going to cancel. So the first term is going to cancel with that. But I don't want to do anything which I regret. So I'm going to do one more step. Just write it out. G squareds cancel out, so I get m squared v naught squared sine squared theta. And then I guess I could have canceled the m squared. Well, too late. Plus or minus 2 v naught m squared g squared. Well, there's one g that takes care of g squared, so it's just g sine theta times t plus m squared g squared t squared. Now I'll get rid of the m squareds first. V naught squared sine squared theta terms will cancel out. So let's see what we get now. This is looking more and more like what you know. Negative 2gy is equal to plus or minus 2 v naught g sine theta times t plus g squared t squared. Aha. Divide both sides by negative 2g. So I get y equals, when you do negative 2g, the plus or minus gets flipped. So minus plus v naught sine theta times t minus 1/2 gt squared. Amazing. We have got the projectile motion equation. Now, the Hamilton formalism gives you this ambiguity of sign always, because mathematics doesn't know that you're launching the projectile up. You could be launching it down. Well, if you launched it down, there's nothing wrong with that. It just means you're on the top of a tall building and you're throwing a ball at an angle theta below the horizontal. So the great intelligence of the Hamilton-Jacobi formalism is that it covers both kinds of projectile motion: above ground firing, where you are on the ordinary ground and you fire it, or you go from a cliff and you throw it at an angle theta. Both of these are covered. Well, since I drew the picture to be like this, I guess I had just something simple like throwing a ball in mind. So I'm going to choose the plus sign. So we'll make a choice. We'll choose the plus sign. So I get the famous equation that Galileo divined using nothing more than the pulse of his hands and very primitive tools. The y equation of the projectile. Now, once you have that, the next, we've done that. Now we have to solve for the x equations. Okay, we have to solve for the x equation. Let's do that next. So for the x equation, you proceed the same way. You do beta x next. Beta x is del s by del alpha x, where s was given here. All right, let's execute. Alpha 1t won't contribute. If I do the derivative with respect to alpha x, I'll just get x. And then again, I have to differentiate because W is equal to all of this. W is equal to all of this. So I have to differentiate that with respect to alpha x this time. When I do that, I get the integral -2 alpha x when I do the chain rule, dy divided by the same thing with 2, just as we had for the other case, just as we had for this calculation here. We're replicating it for the other variable. I'm going to use the same u squared substitution. There's just no change at all. So continue using the same u squared substitution. I'll move this up so you can see the u squared substitution off to the side. So this is going to be beta x equals x minus alpha x. The 2 cancels out. I take the alpha x outside. The minus sign comes outside also. And the integral negative u du. For dy, I'm writing negative u du over m squared g divided by u. Exactly the same thing. So this gives me the 2 negative signs now cancel out. So I get x plus. The u's cancel out. So I just get u when I integrate. So I get alpha x times u over m squared g. And that's equal to beta x. I'm going to call this 2. Now, just like equation 1 down here, equation 2 has some unsavory terms which can be eliminated by using the initial conditions. So we'll play the same initial conditions game. Okay, let's do the initial conditions on this. At t equal to 0, the projectile was rooted to the origin, so x equals 0, which means that the coordinate u, which is over here, because u appears, we need to figure out what it would be at time 0. So u at times t equal to 0 is going to be the square root of 2m alpha 1 minus alpha x squared minus 0. So what is that? Let's figure it out. Alpha 1, we already had. Where was that? Alpha 1 was already here. It's 1/2 m v naught squared. So 2m times 1/2 m v naught squared minus alpha x squared was here. M v naught cosine theta is alpha x. So it's going to be m squared v naught squared cosine squared theta. Well, that's m squared v naught squared in both terms. So I'll take it outside. Square root of 1 minus cosine squared is just sine squared, which take the square root. I get sine theta. So beautiful. It is u naught is just the initial y momentum. No surprise there. Going back to equation 2, I'm going to get beta x equals, remember, x equal to 0 initially. So I'm putting all this at x t equal to 0. At t equal to 0, that equation gives me 0 plus alpha x is m v naught cosine theta. That's just the alpha x is just the x momentum. Where we write it? We wrote it here. M v naught cosine theta. And then u naught is just m v naught sine theta divided by m squared g. Well, the m's cancel out, which is Galileo's famous result that nothing about a projectile depends on its mass. So I get v naught squared sine theta cosine theta, which I can write as sine 2 theta divided by 2. Well, physically interpret this. I'm sure you're all aware that this interpreted physically, it's just the highest point. Beta x is the range. Well, to be more precise, it's a range in the x direction at the highest point. So it's a halfway range. Very nice and satisfying so far. All the initial conditions are interpreted in terms of physical variables. Okay, now we'll go back to equation 2, and just as we did earlier, equation 1 for all time, let's do equation 2 for all time, and that'll give us the information of how x changes with time, or the entire trajectory changes with time. So let's do that. Go back to equation 2 for other times. Then x is not 0 because the projectile is on its way up. So what I'll do is I'll write beta x equals x plus alpha x u. I'm repeating that equation because it might soon disappear from view. Okay, now I'll substitute for beta x. Beta x is that. It's always that because beta is a constant of motion. So I'm going to get v naught squared sine 2 theta over 2g equals x plus mv naught cosine theta, which is alpha x, divided by m squared g times u, which is that square root thing. In that square root thing, the first term without the m 2mg squared gy is going to just be m squared v naught squared sine squared theta. So that I'm going to write for free. I'm not going to keep doing that computation each time. But this time you also have, because the y term is not 0, I have negative 2m squared gy. Well, this time I won't make the mistake. I'll get rid of the m's. So what you have here is one factor of m that's gone, and then this factor of m will go inside the square root and take care of m squared. So now we've gotten rid of mass. Galileo is happy because his experiment at the Leaning Tower of Pisa, dropping a heavy ball and a light ball, is satisfied. Incidentally, I feel like taking a little break. So there's a little mystery about that experiment. It is said that Galileo went to the Leaning Tower of Pisa. It's nicely leaning. So he dropped this heavy and light ball, and his assistant noted something interesting. Assistant said, the lighter ball fell first. Galileo did not believe this, so he asked his assistant to go up and do the same experiment. It's turned out that the assistant was right. The lighter ball fell first. Now we all know that they have to fall at the same height. If anything, it's a heavier ball that has to fall first because air resistance will affect a heavier ball less than a lighter ball. So Galileo, being a very honest, truthful person, made a note in this entry, and people thought, well, maybe it was primitive times and people didn't measure time well. It was not until recently that psychologists showed that it is human tendency to hold on to an heavier object longer than a lighter object. I guess it comes from, holding children or something. If you're holding a child, you don't hasten to drop it. But if you're holding a book, you tend to drop it. So heavier objects, we are hardwired to hold on to heavier objects. So Galileo was super honest and he made that observation. Well, anyway, in reality, all objects fall with the same speed, regardless of their mass. And this is another proof of that. All right, back to the grind. What I'm going to do now to get to the square root is move this lone term to the left and then square everything. Then I get v naught squared cosine squared theta over g squared, and now the square root term disappears. All right. you just have to buckle down and do the math. It's not super difficult math. It's just algebra. And anyway, I'm doing it and you're watching the video, so it shouldn't present any problems to you. Just watch the fun. So using the formula a plus b squared, I get v naught 4. Now sine 2 theta, I'm going to write as sine squared theta cosine sine. I'm going to go back to sine theta cosine theta. Sine 2 theta is 2 sine theta cosine theta. It's just a twice angle formula. So I'm going to go back to that because it's easier to deal with. Because here I just have sine squared. I don't want to see sine squared 2 theta and then sine squared theta and wonder how to deal with it. So I'm going to write this as sine theta cosine theta and then square over g squared. The 2 goes away because of that 2 there. And then I get to minus 2 v naught squared sine theta cosine theta times x plus x squared. On the right side, I have v naught to the 4 cosine squared theta sine squared theta over g squared. Oh, this is brilliant. Now you see why I wrote sine 2 theta as separately sine theta cosine theta? It's because I anticipated this cancellation. Okay, now multiply these two, you lose a factor of g. So I'm going to get negative 2 v naught squared cosine squared theta times y upon g. So much of grad school is just perseverance. Doing the same simple things over and over without getting fatigued is the name of the game. So y equals, let's pull out some common terms, negative g over 2 v naught squared cosine squared theta. And then you have we're almost there. Multiplying through we know v naught squared cosine squared theta, one of the factors of cosine remains in the denominator. Sine over cosine is tangent. So I get v naught tan theta times x. And here I get 1/2 times g over v naught squared cosine squared theta x squared. This equation, this very famous equation, it's known as the equation of the trajectory of the projectile. In other words, it describes the classic upside down parabola. All right, now finally, let's write the complete action. The complete action can be written. We are here. We are in step 7. We've got everything and we're writing the complete action and we'll write the energy and that'll be the last step. All right, the problem is coming to a conclusion. Let's write the final action. S equals alpha 1 times t. Where is that expression for S? Things are all over the place here. So it's this one, negative alpha 1, and alpha 1 was equal to 1/2 mv naught squared. So it's 1/2 mv naught squared times t plus alpha x, which is equal to mv naught cosine theta from here, from the first initial condition. And then w, which is the characteristic function, 2m alpha 1 plus, minus alpha x squared minus 2m squared gy times dy. And I just want to note that this quantity here is just m squared v naught squared sine squared theta. We've already seen that many times. So just keep that in mind. Now I'm going to integrate this. I've avoided integrating it to show you that you don't actually have to integrate it in complicated problems like the Kepler problem or the swinging Atwood machine problem. But in this case, using the same U-squared substitution, it's actually easy to integrate it. So I could have integrated it from the very beginning, but I didn't want to do it because I wanted to emphasize that in this method, the actual form of W is not as important as the partial derivatives of W. And now I'm doing the extra step of finding the energy, therefore I want the S also. So carrying my same U-squared substitution, U-squared equals, now I'm going to write this part as M squared V naught squared sine squared theta minus 2M squared GY, and then 2U du equals negative 2M squared G dy, etc. And I carry out the algebra. I'm going to get that's going to be U times dy, which is going to have 1/2 U du, so the U's will cancel out. I think I should do it. I'm trying to talk myself out of doing it, but I think I should do it. So this is going to be U times dy, which is going to be the 2's will cancel out. So dy equals negative U du over M squared G. I always regret not doing these little things because when I review the video, I think, man, I should have done that. The video is already an hour and a half long. What's another 5 minutes? So I'm just going to go ahead and do it. It's U times dy, which is just this integral part. U du over M squared G. And that's going to be U squared du, which is U cubed over 3. So this part's going to be negative. Let me see. And then I have to replace all the variables. Okay. So that's going to be negative U cubed over 3 M squared G. And now I put the U cubed back. So U squared back. So that's going to give me an extra factor of M because M squared will cancel and there'll be extra factor of M left. And then I'll get V naught squared sine squared theta minus 2GY to the power 3/2 over 3G. All right, done. My conscience is clear and I can write the full S in its full glory. So S, therefore S is equal to S for the projectile motion. Big drum roll, because we're actually able to find the Hamilton principal function completely for a problem, which is usually almost never done. But in simple problems like the projectile motion or Atwood machine, you can do it. The advantage in having the principal function in its full glory is that you can make some grand statements about the motion itself. For example, we all know how the projectile is going to go. It's going to fly and then land in the ground. But suppose we don't know this. Suppose we don't know this. Okay, it could be a very complicated projectile. It could be doing some weird things, air resistance, magnetic fields. You don't know. So let's pretend. Let's play a game. Let's pretend we don't know. The X motion. How can the Hamilton-Jacobi formalism help us? So the idea is to go back to the beta equation. The beta X equation will tell us how. Beta X is X plus alpha U XU over mg. So let's do that. beta x equals x plus alpha x u over m squared g. And it's going to be x plus mv naught cosine theta over m squared g. And now we do have the full, the u function is just m squared v naught squared sine squared theta minus 2m squared gy. Okay, beta x itself, I've done that before already, the same calculation. Sine theta cosine theta over g. I'll take the x on this side, and then I'll get one of the factors of m will cancel out. And now for y, I'm going to put the equation that we had, because the equation for y is known to us. It was here. The equation for y is known to us, so we can put that equation for y there. So I get v naught sine theta t minus 1/2 gt squared. Stay tuned for the next 2 minutes because you're going to see a miracle happening. So this is, I think, really amazing to see. So square both sides, just like we did before. Square both sides. If I square both sides, I'm going to get v naught to the 4 sine squared theta cosine squared theta over g squared minus 2 v naught squared sine theta cosine theta over g times x plus x squared, and that's equal to all this stuff. So that's going to be, you know what, I'm going to cancel out 1m. So I'm going to cancel out 1m from there and the other m from here, so I don't make that same mistake again of carrying the m's unnecessarily. Got to make Galileo happy. So this gives us v naught to the 4 cosine squared theta sine squared theta over g squared minus 2v naught cubed cosine squared theta sine theta times t, because you're going to get that squared and then just without the square over g. And then the last term is going to be plus, because there's a minus there and another minus here, becomes a plus. And the 1/2 and the 2 cancels out here. V naught squared cosine squared theta t squared. This term cancels out. Very nice. Now I can write this as the following. I can write this as x squared, and then this term I can bring to the left. So x squared minus v naught squared cosine squared theta t squared is equal to all the rest. I'll take this to the other side, then it becomes plus 2v naught squared cosine theta sine theta over g times x minus, here I have 2v naught cubed. So I've taken 2v naught squared outside, so I just get v naught times extra cosine theta times extra t. All right, this is looking very interesting indeed. That is a squared minus b squared. I can write it as a plus b times a minus b. So I'm going to do that. I'm going to write this as x minus v naught cosine theta times t, and then bring this to the left side. So that's a minus b. A plus b is x plus v naught cosine theta times t minus whatever I brought to this side, which is 2v naught squared cosine theta sine theta over g. Well, that is just the range of the projectile, because the range of the projectile is the time taken times the x velocity. X velocity is v naught cosine theta, and the time taken is 2 times the time to go to the highest point. Time to go to the highest point is v naught sine theta over g. So 2 times that time is 2 v naught sine theta over g times the x velocity, which is v naught cosine theta. This is none other than the range of the projectile r, what we have called earlier in that figure that we drew, this thing here, the range r. And all this is equal to 0 because we have factored everything on the left side. So brought everything to the left side. What is this telling us? It's telling us that this equation has two solutions. The solution number one is x1 equals v naught cosine theta t. This everybody knows. In a projectile, the x velocity is constant, so the x position of the projectile is just the x velocity initial times time. This is what everybody knows. So this is catch hold of a high school student and they'll tell you this is true. So this is expected. What we don't expect is a second solution. So what is going on? Solution number 2 is telling us that x2, I'm writing 1 and 2, 1 for the first solution and 2 for the second solution, is r minus v naught, because when I put x plus v naught cosine theta times t minus r equal to 0, I'm going to get x equals r minus v naught cosine theta times t. What is this solution telling us? It is telling us how much time, how much distance is left over to be covered. It gives you the how much yet to be covered. So here you can see the enormous intelligence of the Hamilton-Jacobi formalism. It captures the ideas of the entire trajectory at once. It tells you not only what's happened so far, but what's going to happen in the future. So the Hamilton-Jacobi formalism looks at the entire trajectory at once in the phase space. It does not care what you think is more important, whether you as a batsman hitting the baseball, you see the ball leaving your bat and going up, but the fielder who's trying to catch the ball sees a different story. He's thinking about, or he or she is thinking about how much more distance the ball has to cover before. So the Hamilton-Jacobi treats both players in the baseball game equally. It doesn't know which is more important. So this is the beauty and the great power of the Hamilton-Jacobi equation. It gives you a global picture of the trajectory in phase space. So I think that's enough for this example, which is a simple enough example, but it's always good to do a simple example about which you know everything in a new formalism to see how that formalism really works.